Hey everybody, good evening and welcome. My name is Obi-Wan Pez. This is in Simplex Pachinko. We are doing some mathy stuff tonight. Right, there we go. Slightly better, maybe. We're going to be looking at cracking the GRE math subject test by second edition by Princeton Review, copyright 2002. Good news is they haven't really changed the test all that much, so get to run through and use basically the same material that I used 22 years ago to take the exam. So, if anyone has any particular mathy type questions, we will go ahead and attempt to answer them in the order in which they are received. If not, then we use the material that we have here just as kind of like a guide for what to cover next. This is the 10th of June. We are living very approximately at 54 degrees north, and I'm going to tell you, the sun out there is still pretty decently bright. So, I will let you all see what it's like out there on the 21st when we get our solstice, and it's pretty wild. It is currently 10:17 p.m. and that's how light it is. Most people around here have blackout curtains. Our room in the essentially loft of this house also has like blackout curtains over our the Velux windows, which are like they you pull a latch down and then they're a little bit different. So here in the UK, they don't really have a problem with mosquitoes yet. Once climate change really kicks in, they're definitely coming up here. But, there are like a few mosquitoes, but they hardly ever come in the houses. So basically, you click this latch and then pull down, and the entire window shifts into. Yeah, okay. I'm holding it here, right? Shifts down so that you can actually affect how the air flows into the house through these windows. Normally they're on the roofs, so they're like inclined, and then when you open them like this, you can still have like the rain hit them and run off, or interestingly, you can actually pull them even further than horizontal, and it catches the wind and knocks it basically knocks the air into your house. So it becomes rather interesting to predict the weather. Absolutely necessary. All right, so last time we were talking about the cross product of a particular set of vectors. We were using 3-space. This also works in n by n space, so it doesn't matter how big it is. But the point here being that we were able to reconstruct and then prove that A cross B in 3-space ends up being the exact same as a Jacobian of vectors A and B in 3 space. So we have our I hat, J hat, K hat, which are our directional vectors, and then A1, A2, A3, and B1, B2, B3, which are the components of those vectors. And it doesn't much matter, row operations make these equivalent. So put the IJK at the bottom, in the middle, on the top, A and B in whatever order you want. It doesn't matter. It's all going to get you the same determinant. So when we take the determinant of these two, of this Jacobian, then we end up getting the same as the cross product. Okay, so now this brings us to the triple-scalar product, which we no, we did not talk about. Okay, so when we have A cross B, then dotted with C, this is what we get. This will be equivalent. You know what? Let's work on this first. So we have and some vector here A, some other vector here B, and then some other vector here C. We're going to say that C is headed into the page, into the board, however you want to call it. Whereas A and B are essentially on our flat plane here. Okay. So what we're doing here is we're doing A cross B. So here, I hat, J hat, K hat. A1, A2, A3. B1, B2, B3. Which is equal to I hat, A2, A3, B2, B3. Plus J hat, A3, A1, B3, B1, plus K hat. Sorry, these are times the determinants of the other matrices that we see here. A1, A2, B1, B2. Okay, so this is maybe a little bit weird. This one in particular, many of you out there would probably be used to saying, okay, if I want to take the I hat matrix and figure out what the determinant of this particular term, or what the determinant is going to be take the first row and then multiply that particular term, that particular component, with the determinant of whatever's left if you were to cross out the rest of the row and the rest of the column. So here we have I hat times the determinant of A2, A3, B2, B3. Easy enough, right? Well, what in the absolute hell did I do with J hat then? Most of the time, people are trained that they cross this out and they do A1, A3, B1, B3, but wait, there's more. They would need to use a checkerboard pattern to determine, well, let's see, this is plus, this is minus, 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 this is plus. If you circle one of the pluses, it is plus that thing. And if you circle one of the minuses, as we did here, it would be minus j hat times the determinant of a1, a3, b1, b3. However, I got around that. So there's an alternate way of doing this, where instead of looking at this checkerboard pattern and saying like, oh, we need pluses and minuses in alternating places, what we can do instead is say, okay, we're going to start with j hat, and then we're going to take the determinant of the matrix starting with A3. So you start with your j hat and then go diagonally down and in, and then that is your top left corner. And then you say, well, if I want to go right, and I can't go right here because there's a bar there, what we do is we basically treat it like a torus, go back around to the other side, A1. So A3, A1, B3, B1. All right, so when you do that, it's always plus. So I personally like this way better. The cost of changing the columns in this case is that in changing the columns, you would end up changing the sign out front. So it would be a minus j hat times the determinant of a1, a3, b1, b3. But instead, I do it now as plus j hat times the determinant of a3, a1, b3, b1. So, I don't know. I liked it better. Right, and then when we do k hat, this is nice and easy because either way that we look at it, you could say, okay, I want the determinant of whatever's left. Well, there you go. A1, A2, B1, B2. Or if you did it my way, you say, oh, I'm going to go diagonally down and right, but I can't, so I'm going to wrap around, and that's my first term. It's the same thing. We end up in the exact same place. Okay. This is I hat times A2, B3 minus B2, A3. It doesn't matter what order these are in. This is all fine. Plus j hat times the quantity A3, B1 minus B3, A1 plus k hat times A1, B2 minus B1, A2. But wait, there's more. Again. So here, now we have to say, well, we're going to dot this with C1 I hat plus C2 J hat plus C3 K hat. And again, if you remember what the dot product was, here we're looking at the, how did they describe it? The scalar product, yeah, projection. So we look at the projection of the cross product onto C. And The way we would if it's A cross B, we're doing the right hand rule from A to B, so it goes into it doesn't necessarily have to be matching up with C, right? So we have a projection of a particular vector that is going into this space. Let's say it goes to there, then gets projected down. Right, that is a terrible idea. So A cross B is actually the arrow that's in there, but then dotted is going to be the projection onto C of A cross B. Okay, so what does that do for us? Well, that's going to be I hat times A2B3 minus B2A3 times C1 plus J hat times A3B1 minus B3A1 times C2 plus K hat times A1B2 minus B1A2 times C3. I'm sorry, that is not true either, because these don't exist anymore, right? Our hat terms, the directional vectors, were all I squared, J squared, and K squared. So they're equal to 1. Or, I suppose, I hat dot I hat, J hat dot J hat, K hat dot K hat. So they're all just scalars now, they're all just 1. And then now we just have this whole thing, which is the triple scalar product. Okay, now if we remember back to what we were talking about before, we're going to end up with A cross B, which is a perpendicular vector. To the plane containing A and B. And then this dot C well, okay. Not component. Finds the projection of A cross B in the C direction. Now, interestingly, because all of these things are being multiplied in the way that they're being multiplied, we have these multiplications which are then being added together through all three terms. Then we're also having these subtractions which are happening in all three terms. These are effectively prisms. The way that this is going to end up working out is we're going to have our A and B in the plane of our screen here. Then we're also going to have in C in some direction that is going into the interior of, or back behind the screen. What this is going to do is create a not just parallelogram, where we could also find the area of the parallelogram here by doing our, I believe the dot product would suffice. So we're saying, okay, we want the projection onto B of A, which is the dot product of A and B. Right, this ends up being magnitude of A times the magnitude of B times the cosine of the angle between them. Not really where I wanted to go with that, sorry. It's a good reminder, though. What we really want to talk about is the magnitude of a cross B, which is equal to the area of the parallelogram. We did mention this last time. This ends up being equivalent to the sine theta times our A vector. So what we have from above, we notice that we do have A cross B. It's not the magnitude strictly of this, so it does go off in a particular direction, therefore it's not the area exactly. However, when we then dot it with C, we're doing something else. Right, something else is happening here. We are also looking at the projection of A cross B in the C direction. And in doing that particular multiplication, we are going to multiply the area of the parallelogram by, this is the A cross B is its own term now, times the magnitude of C. So we're taking the area of the parallelogram, we're multiplying it by the magnitude of C times the cosine of phi, which we're going to say like is yep, that angle. It's too close. That's going to be a pain in the rear, but so the angle that goes between C and A cross B is going to be that angle. And when we multiply those particular things together, it turns out that this is now going to be equal to the volume of the given parallelepiped, which is like one of the best words ever. Oh, no, LE. Right, so that's going to be the area of the given parallelepiped, which is the uh, defined by a vector, b vector, and c vector. Okay, so all of this taken together is equivalent to taking the A cross B, oops, not, taking A cross B and then dotting it with C. All right. Example 3.1 of the book. Let A be defined as negative I hat plus K hat. B, let it be defined as I hat minus 2J hat plus 2K hat. So A. Find the magnitude of the vector 5A minus B. B, find the vector whose J component is 6 and is orthogonal to both A and B. And C, find the vector whose magnitude is 6 and is orthogonal to both A and B. So with this, we've got 5 times the quantity negative I hat plus k hat minus parentheses I hat minus 2j hat plus 2k hat. Okay, this is going to be a negative 5 I hat plus 5k hat minus I hat plus 2j hat minus 2k hat. Bringing like terms together, we end up with a negative 6i plus 2j and plus 3k. So if we have, say, 5a minus b is equal to this, therefore, if we want to know what the magnitude of 5a minus b is going to be, we need to take the square root of here we just end up taking the term, the numbers individually squared. So here this is going to be negative 6 squared plus 2 squared plus 3 squared. Square root of 36 plus 4 plus 9 very nicely is the square root of 49, which is, of course, 7. And we need to move that back down on the other side. Okay. So now, find the vector whose j component is 6 and is orthogonal to both a and b. So if we want a vector, specifically the positive vector, where we are orthogonal to both a and b, this is going to be a cross b. So we'll worry about this first, and then we'll worry about the j component being 6 after. One of the things that we can do very easily is say, okay, we have a cross b, and then we're going to multiply it by some constant, call it c, and c has to be valued such that the j component is 6. Again, this is negative I plus k crossed with 1, negative 2, 2. Okay, so most expedient way, I think, is going to be we just want to do the Jacobian again, so ijk followed by our A vectors, which are going to be -1, 0, 1, and B is going to be 1, -2, 2. All right, go through it, do the individual multiplications, all that good stuff. So here we've got I hat times 0, 1, -2, 2 plus j hat times determinant of 1, -1, 2, 1 plus k hat determinant -1, 0, 1, -2. All right, is equal to, so we have here I hat, 0 times 2 is 0, so that's fine, and then minus -2 times 1 is going to get us overall a positive 2. Okay, plus j hat times 1 times 1 is 1, minus 2 times -1 overall is going to be a positive 2, plus 1 is going to get us 3. Okay, and then k hat times -1 times -2 is going to be positive 2, minus 1 times 0 is just going to be 0 there. So here we get a 2. Find the vector whose j component is 6. Currently, this j component is 3. So this is a nice, easy one. So if we go down here, this is c times 2i hat plus 3j hat plus 2k hat. So here we know that 3c needs to be equal to 6. Therefore, c is equal to 2. And then that lets us know that the vector as a whole is going to be 4i hat plus 6j hat plus 4k hat. All right, then find the vector whose magnitude is 6 and is orthogonal to both A and B. So here, with the orthogonal to both A and B, we've already done that work, right? This is A cross B, which is equal to, and we had this again, 2i, 3j, 2k. Then we have to make the magnitude equal to 6. So again, here we have a c times our A cross B. And actually, right, c times the magnitude of A times B is going to be equal to 6. So c is going to be equal to 6 over magnitude A cross B. Which is 6 divided by, we had over here, this is going to be square root of 2 squared plus 3 squared plus 2 squared. This is going to be 4 plus 4 is 8 plus 9 is 17. So this is the square root of 17 in the denominator of c. And then here, again, if we want the magnitude to be equal to 6, this is just going to be 6 over root 17 times A cross B. So here, this is going to be 12 over root 17 I hat plus 18 over root 17 j hat plus 12 again over root 17 k hat. All right. If anyone has any questions about that, please let me know. And otherwise, we're going to move on. 6 over root 17 times our vector 2i plus 3j plus 2k. Excellent. And we had our previous one, 4i plus 6j plus 4k. Also excellent. One would hope that I got all this right, but nonetheless. Okay, we're dealing with lines in 3 space, so we want to be able to describe how they work. So individual points certain reference point might be x0, y0, z0. Okay. Similar to the way that in 2 space we can define a single line we can in 3 space still also define a line by 2 points. So if we pick any 2 points, it's, there is only one line that is going to go through those 2 points. Or this time we can't do define by a 1 point and a slope because we don't have a particular slope to choose. Slope doesn't really mean anything in 3 space because now what direction is it actually moving in, and what is its relative steepness? Well, steepness compared to what variable? So we are kind of stuck in that particular respect. However, what we can do is say that this is going to be defined by a 1 point and 1 vector. And then that is going to give us a direction of travel. Now, it doesn't have to be a vector that is also on the line. So this gets a little bit tricky. It's not a big deal, though. Because vectors always originate at the origin, right, because vectors always originate at the origin, this is going to give us a vector that is parallel to the line itself that we want to define. Right, if it does not go through 0, 0, 0 itself. It does go through the origin 0, 0, 0, then we don't have to that means that your point is also going to be on your vector. Which could potentially be a problem, but it'll be all right. Right, in doing this, we would end up with x0, y0, z0, and our okay, so this is going to be our particular vector. We'll call it V. Very imaginative, I know. Right, V1, V2, and V3. So is our point XYZ, we call it just P, going to be on the line L, which again is going to be defined by one point and one vector. We have the 1 point up above x0, y0, z0, and now the vector v1, v2, v3 giving us direction. So is point P, XYZ, on the line L? We'll come right back to that after about 3 minutes. And I'm going to, cycle water, get up, stretch, do all that good stuff, and see you in a few. Thanks everybody for coming. So we were doing some Tai Chi today. Made it through most of the form, according to our instructors. So looking pretty good so far. Anybody who wants to follow along, these are some pretty good stretches and warm-ups and things like that to help you do all sorts of stuff. Usually stay a little bit more limber. First, you have to practice them pretty much every day, but nonetheless. So basically what we do is we let our arms kind of swing around us as we turn. And just keep them close to you. Don't like try and lift them or anything like that. Just let them kind of fly where they may. So we're doing a little bit of like some of the aspects of Stoicism or the Tao Te Ching, which is like, you know, philosophical text. Try and let things flow as they may. And up in the front as well, like this. Again, hands are more or less just kind of flying where they may. We do a little bit of a dip onto the balls of our feet in order to give our arms a little bit more power as we're letting them drop. Just like a kid on a swing, do some pumping, and it ends up with more power, more energy, going higher. And then like this, front foot straight, back foot at 45-degree angle, and then we just shift weight from the ball of the left foot to the ball of the right foot in order to with appropriate time in order to make them swing higher and faster and all that good stuff. And switch. There is also another one that we do sometimes. Where we align front foot moving forward with back foot going at 45, and then lift up the knee on the front leg so that just your toes are touching the ground. Keep most of the weight on your rear ball of your rear foot, and then here we do the same swinging. We tuck into the inguinal creases on either side of the groin, and then stand up as just kind of bend down and then stand up. Again, letting the arms kind of float around you. And it's a really good workout for the rear foot or rear legs quad. It's pretty intense. You can't do it for several minutes on end. But anyway, you do want to continue tucking into the inguinal creases as we do it, rather than just standing still. It really works out that muscle. Same thing on the other side. Tempo of the song is almost right on, so good job. Right on. So, feet in a V shape. Start out, roll the shoulders forward, start a bear stance, and again, tuck into the right ankle. Straighten out the left foot, move across. Straighten out the right foot. In for 2, out for 2. Tuck left, energy ball, turn on the heel of the right foot, and then just lean. Tuck into the right inguinal crease, step with the left, forward off left, straighten the foot. Here, turn on the ball of the right foot, step with the right foot, go to right, forward off right, turn the back foot. Here, turn, tuck into the right inguinal crease, go into roll back, cross, press, push, turn to the front, pigeon-toed, both of the hands come out this way, left one drops underneath, creating tension on the left knee, and then when we snap around and do a single whip with the hand coming out this way, holding here around the sternum, and then we step out, the hand forward, and then when we change weight, when we move the hand around, down, lift hands, come down and back, and then we do a shoulder strike. Then we twist the left foot on the heel, tuck into the right inguinal crease, go to white crane, just barely touching the left toes on the ground. We go into brush knee. Step up. Barely touch the heel to the ground on the left. And we're in strumming the lute. Do another brush knee here. Okay, lean back. Turn 45 with the front foot. Lean forward again, making a fist with the right hand. Turn, twist step. Come around. Punch. Then we do a Rufung Subi, tucking into the left inguinal crease here. Take the weight off. Back, forward and push. Back again. And pigeon toe to the front. Break. Round. And mostly weighted on the left hand side, and our left hand is not supposed to like be essentially holding itself up. It's kind of hanging on the right hand. Right hand is doing most of the work there. Okay, then come like this, turn on the heel of the right foot. Left hand is up around the ears. Take a big step back diagonal. Then as we come through, we're going to bring both hands around. Very Tiger Mountain. Right hand comes up, roll back, press, push, turn again. This is the exact same move we did over there at the very beginning. And we come back around like this and whip. Then from here, we're going to go to the corner of the room. Forward, back, turn the foot to the wall, and then we whip hands around to either do like a double block or various other things. Take a step the right with the right foot, and then we come forward and push the left hand here. We want this to be basically no weight on the front foot, which is hard since we're trying to like move forward a bit. Right, then from here, do repulse monkey. So this comes back around this way. Step back, toes hit first, then the heel. Trying to keep our foot straight, which is really hard for me. Back around. That again. Right. From here, we reverse direction of hands. Another step back, turning 45 degrees the other way. Press up like this. Again, here, this is essentially starting from this position and pushing out. This is coming down, this is coming out. And then we want to be lent on the right leg here. So, doing this all together. Okay, tuck into the right inguinal crease, make energy ball here. Step left gently. Ward off to this side. Step right together. Do a ward off to this side. Step left. Ward off to this side. Step right together. Ward off to this side. Step left. Do a ward off to this side, and then step forward with the right foot and do a ward off to the front. From here, we tuck into the right inguinal crease and do essentially what's going to be a whip here. And then we turn into it this way. We step left and then lean forward again from this side. Reach down, grab somebody's like back of their calf or pant leg, something like that. And then we come up, block, switch, block the other way. As we come down, go around. This is essentially going to be a block with something over here, and then striking out at their face over this side, or it can also be a block or various other things. Right, our feet are currently too far apart, so we do a rollback, turn with the right heel this way, tucking into the left inguinal crease. Hand comes around and turn on the right ball of the foot, which now gets us in essentially like a little bit more like a cat stance. Feet are way closer together. And then we up. Left hand is performing a block up here. Right hand is sweeping something away from the leg or doing a block up here somewhere, but lower. Step to the right. And then we want to do the exact same thing on this side. And then we do another rollback, tucking into the right inguinal crease here. Come around, step, cat stance again, getting hands back around, and then higher on the right this time. Toe kick. We're going to step backward, such that our heel on the right and our toe on the left are in roughly the same position, and then we turn on the left here. Right heel and left toe, I believe. Yep. That was it. Come back around to this side. I'm going to block left and do a heel kick here. And as we come down, a knee brush knee. Then, once we do the brush knee here, lean back, turn the foot 45 degrees, do a brush knee to the other side. And then same thing on the other side here. Back, turn the foot 45 degrees, step left, and we're going to do a twist a little bit, but this is essentially going to be a gut punch, or especially into like the bladder area. And then this is also a brush knee on this side. Then straighten up a little bit, turn the foot 45 degrees again. This time going to ward off, roll back, press, push, just as always, same exact thing. And then once we get here, this is where I usually stop. We did learn a few extra steps today. So from here, we do something called Fair Lady's Hand. Transition to it, also a very good question. Damn it. It's only been a few hours. Come on, man. So we go to energy ball here, turn the left foot in so that we're pigeon-toed again, and then go on the right toe so we're facing kind of 45 degrees direction. It's right there. And then we step like way around to the other side. Come around here. Then as we step left again, we're going to both come up the left arm as like a block, and also the right hand in as either a block or strike. Like that. And then we have to do the exact same thing again. So turn on the left heel, go this way, all the while we're coming around opposite energy ball this way, and doing the same thing here. Stepping out here. Right sort of up block, and a left follow through the okay, go single whip this way here. Turn, left hand comes down, turn this way. Right foot here. Side step. Okay. Well, I think that'll do it for now. Oh, did we lose internet? Hope not. Now I'm just confused. Fine. Oh, I guess we're good. I don't know what happened. Good times. If anybody wants to do martial arts, highly recommend it. Very good. As long as you get the right place. It's very good physical activity and also keeps your brain going. Right, so is the point P, XYZ, on the line L? So if it is on the line L, okay, so if P is on L, then if we were to subtract P0, it will go down to the origin. Right, so P0 minus P0, it should be the origin. Our zero vector, or I guess we could call it the zero vector right here. And so if that happens, then P should also go over to some projected point over there. So that P minus P sub 0 should be equal to some point that is on V. Right, and then how do we describe that? Well, it should be some scalar value multiplied by V1, V2, and V3 equally. So we're going to do like, C V1, C V2, C V3. Don't know what it is. Could be positive, could be negative, could be just about anything. So as long as it is a scalar multiple times all three of the coordinates in V, then it will be a scalar multiple of v, and therefore p would have to be on L, the original line we started with. Okay, so this point over here should be p minus p0, and then it should also be some particular point on v, which again we found below. Let's see, they also mention that we could find the dot product. So the projection of p0 onto p should also be of a vector to p0 onto a vector to p. Oh, no. Never mind. It's not a dot product. I was going to say that looks really weird. Okay. We're good. We can ignore that. Or a line L can be defined by a set of three parametric equations first of which being that if we had x minus x0, that should be equal to cv1. If we had y minus y0, it should be cv2. And if we had a z minus z0, it should be equal to cv3. Okay. They also said, let's instead make this x minus x0 over v1 is equal to c, but also y minus y0 over v2 is going to be equal to c, and also z minus z0 over v3 is going to be equal to c. So in doing so, we now have all three of these equal to c, which is the same parameter, and now we can just get rid of that and say, nah, it's just x minus x0 over v1 is equal to y minus y0 over v2 is equal to z minus z0 over v3. For v1, v2, v3 equals 0, omit them. And these are going to be called symmetric equations. This allows us to work with any particular This allows us to work with any particular part of these symmetric equations to describe the distance that we're traveling between x and x0, and then normalizing it by the component of v that is that corresponds with either the x, y, or z coordinates. Naturally, this also works with higher dimensions. We'll just usually say x1, x2, x3, and then continue on up. All right, so examples. David Jones, how's it going? Good evening, welcome back. Right, so where does the line that passes through these 2 points end up piercing the xy plane? So the xy plane is where z is equal to 0. Everything coming through okay? Yeah, okay, we're good. And again, just because I'm paranoid, check desktop audio, and it is not playing music on stream. I mean, it is for you all, just not later. Gotta watch those. Okay. So this is talking about stuff that literally we just were talking about. So right, if we have, let's just do this real quick. Okay. X, Y, Z. This is a -3, -1, +2, and a 5, 8, 4. Hopefully you kind of get the point here in terms of like the depth of field. Right, so where... Oh, right, yes. It does eventually cross the XY plane, just not between P and Q. Um, all right, so this is going to be... Right, so this is going to be parallel to that. This is going to be our V. We want P, go back to the origin. We want this particular thing to be projected onto this line. It's going to be C. Right. This is going to end at some particular value. We don't know what it is yet, but whatever, it's fine. Right, actually, we do know what this is. We'll call it here. Right, then this must be CV to get to that particular point. So if this is our origin, then V is going to be equal to Q minus E. Right, the vector that goes from origin to P and origin to Q. This thing that we've got here is going to be Q, but then we subtract the P vector. Right, subtracting the p vector, we end up going backwards here from our q vector here. Right, q negative p. Okay. This means that we're going to take q, which is 584. We're going to subtract p, which is -3, -1, 2. So the 5 minus -3 I hat plus 8 minus -1 j hat plus 4 minus 2 k hat. Right, so that's q minus p, which is, this is 8 I hat plus 9 j hat plus 2 k hat. Okay, which is also known as v. So then we need some sort of c v c I hat plus 9 c j hat 2 c k hat. Maybe I didn't need to do that overall, but okay. But c v hat plus p again is going to get us to that particular point, which we might as well just call r, because that's the next alphabet letter. So right here, it's going to be r. Point, right? The individual point r is going to be 8c, comma 9c, comma 0. No, not 8c and 9c. 8c plus p1, comma 9c plus p2, comma 0. And that 0 is also going to be 2c plus p3. This is how we solve stuff. Okay. We have an in at the moment. So this is going to be 8c plus p1 is going to be -3. Bracket with I hat. Okay, plus bracket 9c plus p2 is -1 j hat plus 2c plus p3 is 2 k hat and again 2c plus 2 needs to be equal to 0 to get us back to R. So if we call it R vector, that's just pointing to the location of R from the origin. That'll be fine. Doesn't really matter. Either way we do it. This is going to get us a -1 for C. Wait, was it? Oh. That's right. Q was higher. P was lower. So actually it should have been on the close side where it ended up hitting y or z equals 0. Oh well. Okay, so -9 plus or -1. -10j plus 0k. 8c is a -8 minus 3 is a -11i. It's going to be r. So this is what we want there. What was the actual question? Where does this line pass through, or where does it pass through the xy plane, given that it passes these 2 points, P and Q? So, yeah, this is the vector, therefore R is going to be -11, -10, 0. Really, it's that, not that one. Slight pedantry, but you know what? It's fine. All right. What else we got? -11, -10, 0. Nice. We did it. Okay, so planes in 3 space can be determined once we know a particular point on the plane and a vector that is perpendicular or normal to the plane itself, which tells us the plane's orientation in 2 of the dimensions, right? Because if we just think of it as the lines themselves, we have a point on the plane and a line, then the plane can still tilt on that line. So we need a second line somewhere else. We need a second vector, which is not equivalent or not scalar multiple of the first. Perhaps we could even call it linearly independent. So to define planes, we need a point and 2 vectors that do not I mean, is it really just like any 2 vectors? Because if you get parallel lines, it can define the plane. I think it goes without saying, but need a point and two vectors on the plane. That do not coincide for more than one point. So kind of weird, but whatever, it's fine. It's like we end up with a vector here and a vector here that is parallel to it, then that's going to define our plane still. If we have two vectors that go something like this or whatever, fine. That's also fine, right? Because these two things are going to define our plane. We need, effectively, we need three non-collinear points, right? In this case, we've got one intersection and two others to define rays or lines or whatever else we want to call these. An angle. Right, these are defining an angle because now we have rays going off from a single point. And then for expediency's sake, especially considering what we've been just talking about, this was, oh, okay, well, we'll take some point P0 which is orthogonal to the plane itself or normal to the plane itself, and then we get that normal vector there. All right, we're going to come back in 3 minutes. Got an ad break here, so thank you everybody for coming, and we shall return. I suggest getting up, stretching, get some water, cycle your rest of your water. Yeah, see you in a few. And as we usually do here every so often, Jocelyn hoist. We have these 20-pound weights, just under 10 kilos, and typically the just over 9 kilos. Order of the day is do some arm curls until we reach failure, and then do a few shoulder lifts, I guess, and then some overhead stuff. Once we get all that done, we got a good workout for our arms, because quite frankly, they're a bit noodly. Gotta firm them up. They've always been noodly. It is really warm in here too. Yeah, that's good enough. Let's lift straight up with the deltoids. Enough. There. Right. Mostly work out the triceps a bit. And make sure you don't smack yourself in the back of the head. Done it a few times. Not very pleasant. Especially with a 20-pound weight. Alright, good enough. Hopefully on Friday we're getting our boom for the microphone, so it won't just be sitting on the desk anymore. I can actually like adjust it and stuff. Maybe have it over here in space. We'll see how that goes. Alright, so P0 is still going to be our x0, y0, z0. P is still going to be x, y, z. N vector is going to be n1, n2, n3. You know what? Sorry. Okay. If P is on the plane, very unfortunate problem here. We can't use P as the name of the plane, but whatever, it's fine. Then the vector P0P will be orthogonal to n, the normal vector of the plane at that particular point. Right, so at P0, realistically, anywhere on the plane. So the dot product of n and p not p, but P0P as a single vector will be equal to 0. Or, wait, no. If it's a dot product, it's scalar. So it will be equal to 0, the number 0. Vector P0P will be x minus x0 I hat plus y minus y0 j hat plus z minus z0 k hat. And P0P as a vector is going to be equal to that. And dot P0P must be equal to 0, so therefore this needs to be x minus x0 and 1 plus y minus y0 and 2 plus z minus z0 and 3. With all these things getting shifted around, this is going to be n1x plus n2y plus n3z is equal to n1x0 plus n2y0 plus n3z0. So therefore the yeah, I already gave it away earlier. And anywhere on the plane. Right? So here it makes complete sense. This is n dotted with p, and this is n dotted with p0. We took the long route by looking at what the book was trying to explain, but we know what it is. Right? We literally just worked it out right there in that one statement. Yeah, n is the normal vector to the entire plane. So therefore it will be orthogonal to p and p0 and any other particular location. Sorry. This is not necessarily going to be orthogonal, right? Because this is going from the origin to p as a vector and from the origin to p0 as a vector. So it's not necessarily going to be, they're not going to be 0, right? N as a normal vector to the plane is not necessarily a normal vector to the vector p or the vector p0. But again, right, the projection of n onto any vector from the origin to a vector on the plane. What are you doing? No. I can give you permission to do that. Those. You liars. I have a process that's taking up 8 of my CPU cores, so I'm not happy with it. I also requested that the entire process in the window be suspended because I'm doing something else, and that one process is eating up some processor stuff. Hey Stooky, how's it going? Uh-huh. Leaving probably 2 cores for everything else, give or take. And OBS does not like sharing, so. um, okay, so the projection of n onto any vector from the origin to a vector on the plane, on the given plane. Come on, is the same. All right, we are going to manually restrict this thing. I've already complained to the people who run this project that like it's like running shadow in the background. I don't like it. Um, um, how can I limit CPU and RAM for a process? Ask Ubuntu. Be warned, here be dragons. Hooray. That's fine. Probably won't completely destroy the rest of my computer. It's fine. Okay, so go with that. Say CPU limits minus L 200. Let's even give it 200. Process ID. Process not found. Oh, you're cute. That's not what I... What? It's not what I requested. Killed some other random process. That's stupid. telling it to do something to a specific process, and it's pulling a completely different number. That's so weird. I hate it. And it's a different number than it did last time. And it's a different number in both cases compared to what I actually wanted it to do. Process number, whatever, detected. Process number, same, dead. That's not what I asked it to do at all. This is so ridiculous. Anyway. Well, we're never going to get that right, so. And yes, I know, certainly not with that attitude. All right, well. This other process doesn't exist, or command. Whatever. I guess this was 5 years ago that this conversation occurred, so may not, this particular thing may not exist anymore. Anyway. Right, so test problem. Example. Hit it here. Not here, just, that. I think I'm going to suspend this process entirely. This is stupid. Wow. It says it's running with 12 CPUs. This is the same problem as before. Ugh. Spend that. Oh, you jerks. Now it's suspended to two different processes, both of which are totaling now approximately 1,000%. Yay. What are you doing? Okay, so next question. How do we kill a process that says it doesn't belong to us? Yeah, it's gonna take too long to figure out. Knock out a couple of other processes, but so ridiculous. Find the equation. Right. A 4 1 2. B 1 5 4. C -3 2 6. Okay. So again, here we want to essentially say, like, okay, since we have three three points, we want to define two vectors. So, like, ABC, we do AB, BC, or I guess BA, BC. It's fine. BA is going to be 1 minus 4, comma, 5 minus 1, comma 4 minus 2. And then BC one. It's the other way around, isn't it? No. B. Yeah, it is. Right. 4 minus 1. 1 minus 5. 2 minus 4. BC, same deal. Negative 3 minus 1. 2 minus 5. 6 minus 4. 3, negative 4, negative 2, and negative 4, negative 3, 2. Normal vector is going to be those vectors crossed with each other. If we do BA cross BC, get IJK 3, negative 4, negative 2, negative 4, negative 3, 2. Take the discriminant, and so we get I hat times, nope, discriminant of negative 4, negative 2, negative 3, 2 plus j hat times the discriminant of negative 2, 3, 2, negative 4 plus k hat discriminant 3, negative 4, negative 4, negative 3. Which is I hat times negative 4 times 2 is negative 8 minus positive 6 negative 14 plus j hat 8 minus 6 is 2 plus k hat negative 9 minus 16 is negative 25. Okay. The equivalent equations should be x minus x0 over v1. Wait. Those are lines. Doesn't apply to planes. N times x minus x1. N1 times x minus x1. Plus n2 y minus y0 plus n3 z minus z0 equals 0. So here we have a plane, generic plane. This is going to be a negative 14 x minus, and here x0, you just let it be b, I guess, 154. This one plus 2 y minus 5 plus this is going to be a minus 25 z minus 4 equals 0. Oh. Oh no. I got plus 14. Where did I go wrong? But a negative 2 and a positive 25. So I'm exactly backwards as they got. Okay. This is negative 14x plus 14, 2y minus 10, 25z plus 100. The 0 is 90, 104. Nice. Okay. I get the exact same value. It's going to be negative when it goes to the other side, and all of the x, y, z stuff is negative compared to what the book has. Negative 104 when we move it to the other side is going to be opposite what this has, which is 104. So yes, this is an acceptable form. Essentially, this is your like point slope formula, but for a plane instead of a standard line. Okay, cool. Anybody have any other questions? Anything they want to know about? pause the process like that. There is currently nothing running. Okay. Nothing running right now because nothing has been downloaded from that particular project. But the second something gets downloaded from that project, it's going to take over and run in the background. Yay. Could be one of the reasons why my computer's crashing every so often. Alternatively, that only happens because I'm doing something in Elite Dangerous when an update has occurred and I haven't restarted my computer. So I guess that's possible. Yeah, we'll call it there because the next section's on like cylinders and other geometric figures. So we'll do that next time. I'm probably gonna hop onto Elite Dangerous for a little bit. Make sure things have been delivered properly or something like that. The sun keeps teasing you. It keeps following you. You should yell at it, tell it to go away. It's the clouds. I see. Understandable. We've had a week here of like on and off weather, which is of course is natural for England, but yeah, there's a lot of weird stuff going on. You want it to stay out for 20 minutes at a time? Yeah, that'd be nice. Don't let you go dress and then go hide again. I mean, there's nothing else for it. You just gotta like decide that you want to go somewhere and then go there. Something that is really big here apparently and not like anywhere else or not in the United States, unless you're a hiker, is going to like Columbia or wherever, you know, sportswear and getting rainproof pants or trousers as they would have it here. If you ask for rainproof pants, they probably laugh at you. All right, we're gonna go and raid over to Shark Geek, who is doing Water Wednesday, combating shark misinformation. So we're gonna head over there. He did just start like literally a minute ago, so there's pretty much nobody there, but we'll do it. So yeah, we have loved our rainproof trousers. Bring them on every vacation, and like you just put them on, and make sure that your footwear is waterproof, and then like you don't get wet no matter how much driving rain is coming at you. It's crazy. All right. I will see you all tomorrow for more TTRPG prep. We're doing more work on trying to figure out where this campaign is going. Some of my players are potentially leaving soonish. One guy has his spouse is having a baby, so like he's gonna be potentially disappearing for a while. He's also the damage dealer. our uh, two technical people, our sciencey minded people, are off this next week. So I was like, okay, how about they work in the lab next week, and then you guys can go off on an adventure in the town. But we'll see how that goes. Anyway, hope